Hello and welcome to the 13th and final part of a series of videos aimed at developing a Street Fighter game in vanilla JavaScript using the canvas element. My name is Anthony, and please join me in my corner of the web where I like to build retro games in the browser using the latest technologies. We've come a long way over the course of this series. We've built all the basics of a Street Fighter game, such as the fighters, the stage, the status bar HUD, and everything they fundamentally do. But along the way, we've hopefully understood how we bring a professionally looking game to the browser, using its technologies and the canvas element. There are several things missing that we could add or extend, to be fair, such as CPU controlled fighters, which I know everyone is crying out for. But unfortunately, that's one we'll look to come back to another day. Although most of all, and specifically for today, is special moves, and how you'd perform the unique input sequences these require to execute them. Let's bring up our dreaded to-do list for one last time, and pull out the items we'll be tackling in this video. We'll start by adding the infamous Hadouken special move to the state machine just like any other move. But this time, as special moves are specific to fighters themselves, we'll do this through their classes instead, rather than the superclass. As you can expect, for this to work properly, we'll also need to add a new fireball entity to the scene too. In turn, we'll need to animate this, and make it aware of other entities causing collisions and potential damage. Finally, we'll then look to understand how to inspect and keep record of the player's input, so that we can compare it to a known set of special move sequences. If the players perform the correct set of inputs, they'll execute the necessary special move. So, once complete, this should wrap up the video series quite nicely, hopefully giving us a perfect foundation to build upon, regardless of the direction we take it. And just before we move on, if anyone has enjoyed this video or this series as a whole, can I please ask that you like the video as thanks, especially if you've learnt something along the way. Although if you prefer, why not go the extra mile and subscribe? This would also be hugely appreciated too. Both of these take minimal effort and will help me boost the channel in YouTube's algorithm and ecosystem. It'll also let me know if you want to see more of my game related content and push me further to improve it. For those of you who have already done so, either in this video or one of the others, a big thank you goes out to you. Okay, and with that, let's get on with today's video. Before we start delving into today's main topic, we'll first look to fix the camera to make it act more like the original game. In the last video, we implemented a sliding behaviour for the fighters when they were attacked. I mentioned at the time that the camera did not scroll as expected when they hit the sides of the screen, but it did in fact help us test the sliding mechanic more easily. Although to move forward, we'll jump into the camera class and make some minor adjustments. If we look at the update function, it's doing a number of things to adjust the camera's position according to the fighter's position, attempting to keep them in view. We want to focus on the middle section here however, where we're currently moving the camera's X position based on the fighter's X velocity. Generally this will be fine for most push-based scrolling games, although for Street Fighter, it now doesn't hold up. So let's take another attempt and instead purely focus on the fighter's X position and adjust the camera's X position based on that, and in doing so simplifying this section of code somewhat. As discussed in part 8 of the series, the camera has two 100 pixel boundaries on each side of the screen. This value is presented as a scroll boundary constant, which we are currently using in a single if statement here, which includes these two conditions. Taking a note of them, we'll replace the current code and break them out into their own if statements now. Starting with the left boundary, we'll simply set the camera's X position to the fighter's X position, deducting this scroll boundary constant if they are within this section of the screen. Likewise, if the fighter goes within the right side area of the screen, we'll add the scroll boundary to the fighter's X position. Just like before, we're using the canvas's width value as a base for this boundary. Before moving on, notice the time variable is slightly dimmed because it's no longer being used within this function. So let's use a common convention and replace it with an underscore. This tells other developers that this parameter is unused. With this simple refactor, let's take our first look in the browser and see what this has accomplished. As Ken reacts to Ryu's attacks, he slides away as per normal, but this time, if he hits a screen scroll boundary, notice how the camera is now scrolling as expected. Although if he does hit the limits of the stage, the sliding momentum is still transferred to Ryu, very similar to the behaviour of the original game. Nice, the first win for today. With that small correction complete, let's move on to providing our fighters with the ability to perform special moves, specifically in this video, the infamous Hadouken, or as it's commonly known, the fireball attack. As we've done many times before, we'll start by opening up the fighter's constant file again and adding its new move property to the fighter state enum object. Although, as this object is generic across all fighters, we can't use any specific names, so instead we'll use a generic name, Special 1. And before moving on, let's also add this property to the hurt state valid from array 2 at the bottom. Now, over in the Raya and Ken classes, we'll again add the necessary frame and animation data. And I'm sure you've all heard this many times before, but I'll be copying it from my predefined code, rather than typing it out manually. And just to confirm, both Raya and Ken's moves are exactly the same here too. With those in place, we're now going to break tradition and do something a little bit different. As all special moves are specific to the individual fighters, rather than continue as we normally do and add the state to the state machine within the fighter class, we're today going to extend it from the Raya and Ken classes themselves this time around. So in the constructor, we'll set up the special one state individually, following the usual structure as before, adding a new init and update functions. The reasoning for this comes back to the inheritance topic we discussed way back in part 3 of the series. This allows us to add moves and behaviours specific to individual fighters without blocking the generic fighter class unnecessarily. Although luckily for us, both Raya and Ken have exactly the same moveset in the World Warrior edition of Street Fighter 2, so we can simply copy this code between both classes. We should look to also extend the state's valid from properties here too, as we can't do this within the fighter class either. In this example, notice we're extending the idle state to allow it to transition to the special one state, so we're setting the valid from property manually by spreading the default values back onto it. And for the moment, add the usual reset velocities call within the init function, and the animation completed check within the update function. To ensure everything is working as intended, we now need a way to execute this new special move. Normally this would come as a sequence of moves from the input device, but let's not get ahead of ourselves. For the time being, let's open up the fighter class and simply exchange one of the standard attacks instead. In the handle idle state function, we'll commandeer the light punch for now, commenting out the current change state call and replacing it with a special move we've just set up. Okay, with that, let's open up the browser again and see what's what. And good stuff. As we press the light punch button, it seems we've lost the light punch attack, but instead we've gained a special move in its place. This plays out just fine, although there are a number of things we're missing right now, outside of the obvious fireball spouting out of the fighter's hands. Namely the classic Hadouken voice sound, which is not currently playing, and also the shadow beneath the fighter's feet, not stretching as necessary. Let's look to quickly fix these first before moving on to the actual fireball then. We'll continue where we left off in the last video and add the voice sound effect first. Visiting the sound resource website once again and navigating to the Street Fighter's page, we'll download the voices archive this time around, rather than the actual sounds. Just like before, we'll use the overly large green button to do this. Once downloaded, we'll open up the zip file, where you'll be given a whole set of WAV files presenting the vocals for the various parts of the game. However, for us, we can ignore all of them at the moment except for the 74H file, as this is all we need right now. So let's extract just that file to our project sound folder, and let's jump back into VS Code. Taking a look at the sound folder here, you'll notice that we've gone ahead and renamed the file to Voice Hadouken and converted it into an OGG file. Both of these changes are completely optional, but if you follow the last video and its refactoring section, you'll understand why we've done this. So for anyone who's interested, please refer back to that if you need it. Either way, with the sound file available, we'll now add it to the HTML file next, so that we have it available to us in the game. In fact, at the bottom of this file, we're going to actually need two references to it, one for Ryu and one for Ken, giving them unique IDs. We'll do this so each fighter has its own individual sound file they can use, as this removes any collisions the game would have trying to play the same sound back. Next, within the Raya and Ken classes, we'll now add a new property called Voice Hadouken, so that we can get a reference to the audio file using the query selector just as before. Then in the handle Hadouken init function, we'll simply use the play sound function to play the sound as the move is initiated. Straightforward enough. Although, before moving on, let's not forget to make the same changes in both classes. Let's now change our focus to correcting the shadow. In the original game, the shadow would seem to be a different sprite or frame of animation when the fighter stretches out to initiate this special move. Although, as we've done previously, we can actually lean on the canvas's transform and scaling functions to get the same effect, resulting in saving memory. To implement this, we'll add a new property to our state machine, called shadow strangely enough. This will be used to provide the shadow unique properties for each state, if we choose to use it. We'll be using another array, where it will hold a set of 4 values, similar to how we store the animation frame and hitbox data. Although for this property, the first 2 values will hold the X and Y scaling values, to allow us to scale the shadow as necessary, while the last 2 will hold the X and Y pixel offset values, so that we can position it correctly based on the new scaling values. For this state and animation, we'll use a scale of 1.6 on the X axis, giving us 60% more width, but leaving the Y axis with a value of 1, which is the default. Then for the offset values, we'll use a value of 22 on the X axis, but leaving the Y axis to 0. Let's not forget to add this to Ken's class too, to keep them consistent. Now in the shadow class, we'll make the necessary changes to make it aware of this new property and its values. We'll first take a copy of the current scale logic within the draw function and replace it with an array destructor, pulling out the new scaling and offset properties we've just set up. Although to cater for all scenarios, we'll pull these from a new function called getScale, and as we know this new shadow property is sparely used at the moment, we'll give them all their default values. Before we create the new function, let's quickly accommodate these new values in the drawImage call, adding them to the destination arguments. Let's go ahead and create the getScale function now, and add the different variations of the shadow we'll use, starting with the one we've had up till now. We'll check if the fighter is in the air by comparing their Y position to the stage floor constant, because if they are, we'll paste in the code we removed earlier, as this scales the shadow depending on how far the fighter is away from the ground. We'll set this to an air scale variable and return back this value twice within an array, presenting the X and Y scaling values. Next, we'll check to see if the fighter's current state has the new shadow property. If it does, we'll instead pull those values and return them back. The only slight addition here is that we'll apply the fighter's direction to the X-axis offset to ensure it's correctly positioned based on the way they are facing. And lastly, if neither of those are true, we'll default to the standard 1:1 scale. Okay, with those two quick additions, let's take another look at the browser to see what we've done. And when we press the light punch attack now, the fighters now proudly shout their iconic phrase, while the shadow beneath them is stretched correctly, covering their stance. Great stuff. With those fixes done, let's get down to business with the actual fireball now. When I say fireball, I just realised I'm assuming everyone is familiar with what I mean, but just in case you don't, it's ultimately a projectile that spawns from both Ryu and Kan's hands when they perform this special move. This goes across the screen from the fighter in the direction that we're facing, with the hope that it collides with the opponent, causing damage. What does this mean to us then? Well, we'll need to add a new entity to the scene, similar to what we've done with the hit splashes previously. So let's start by adding a new fireball class and a file to our entities folder. I'm going to add this to a new folder called Special, just so that we can group these together. Let's go ahead and set up the class now, starting with the constructor. Here we'll need the fighter instance that spawned the fireball, and the strength which relates to which punch button was pressed to initiate this special move. The time object and the on-end parameters are standard entity arguments we use for all entities within the battle scene, again as seen in the hit splash entities. We'll continue to set up the local class properties now, but in regard to its strength, this needs to be translated into a velocity. So before we continue, we'll next add a new constant file called fireball, which we'll use to set up some constant values for this class. Specifically for the velocity, we'll need to add a new lookup object called fireball velocity, and add each punch attack as the keys. The reasoning for this will become more apparent later in the video, but for now, we'll give them some guesstimated values, with the light attack being the slowest, while the heavy attack being the fastest. Back in the fireball class, we'll now import the Xenom object and use the strength parameter as the key, marrying up the required velocity value. Continuing on, we'll add the remaining properties needed to set up the fireball instance. For the positioning, notice we're offsetting the X and Y values so that the fireball lines up directly with the hands of the fighter when it spawns. As for the image, for whatever reason, I decided to use Ken's image, as it has all the necessary fireball frames we need. With that in mind, we'll go ahead and add the necessary frame and animation data too, which yes, again, I've copied over from my code I prepared earlier, so by all means pause the video if you'd like to copy them. The other thing of note is the animation object uses the fireball state Xenom object we've yet to set up, so let's jump back into the fireball constant file first and add that there. The fireball state can only ever be one of two states, active or collided. I suspect these are self-explanatory, but for the collided state, we'll also need to know what the fireball collided with, if anything, so we'll add another enum object called fireball collided state, which will give that information. The none value means the fireball has travelled across the screen without hitting anything. Returning back to the fireball class, we can now add the required update and draw functions, passing on the usual parameters in each. For the draw function, we'll cheat a little and copy the code from the fighters class's draw function, as the code we'll need will be very similar. We will, however, need to update the references, removing the this keyword from the animations and frames variables, and also the hurt shake from the X destination in the draw image call. Moving on to the update function, we'll add calls to two further functions, one for the fireball's movement and one for its animation. Starting with the update movement function, we'll give the fireball its motion on the X-axis, using the velocity and direction variables, along with the game time object, as we've done before. Next, we'll add a simple boundary check for both the left and right edges of the camera. We do this because we want to destroy the fireball by calling the onEnd function if it goes out of these bounds. For the update animation function, we'll do what we usually do for our entities, and return early if the current animation timer or frame delay has not yet elapsed. If it has, we'll increase the animation frame, but if this is higher than the animation length, we'll reset it back to 0, cause the animation to loop. And finally, we'll set up the next animation timer by using the current time object, plus the frame delay multiplied by the frame time. And for some reason VS Code has been a little silly, so I'll just quickly fix the input paths here. Oh, and yes, while we now have the fireball state enum object, let's give the fireball the active state once it's initialized too. Next, back in the Ryu and Ken classes, we'll set up a new fireball local property to store its current state. This object will hold a fired and a strength property, which will have default values of false and undefined. We'll add it to the top of the class and within the handle Hadouken init function, which we'll come back to in a second. Now in the handle Hadouken state function, we'll check to see if the fired property of this object is false, and if we're on the third and last frame of animation for the special move state. If so, we'll set the fired property to true and look to spawn a fireball using the new fireball class, although we'll need access to the add entity function from the battle scene class to do this. So let's add this function to the constructor and assign it to a local class property. Back in the battle scene class then, we'll now go ahead and forward the add entity function to the fighter instantiation within the get fighter entity function, giving all fighters access to this function if they wish to use it. Let's go back to the Ryu class and complete the add entity call following its parameter list, passing on the fireball class and the time object as per normal, but specifically for the fireball class itself, a reference to this fighter and the strength property from the fireball object. Before moving on though, let's not forget to copy these changes over to the Ken class too. Finally, we just need to set the strength property for the init function. I left this till last as we really want this property to match the punch button the player pressed, although we currently have no way to do this. So for the time being, we'll just use the medium punch strength to test out the changes we've made so far. So opening up the browser and pressing the light punch button this time around should spawn a fireball with a medium strength velocity, and thankfully it indeed does. We are missing the collisions however, as the fireball is going straight through the opponent, so let's implement that next. In the fireball class, we'll create a new function called has collided with opponent. As you can expect, this will look to return true or false if the fireball has collided with the opponent. Let's first get the collision box dimensions from the frame data using the current animation frame. Then we'll convert these dimensions to an actual hitbox using the utility function getActualDimensions we created previously. As we'll be comparing the fireball's collision box with a fighter's hurt boxes, we'll jump back to the fighter class and copy the code from the update hitbox collided function where we do this already and paste it here next. We'll now make the necessary changes to the code so that it aligns to the fireball class's code. First removing the hurtbox parameter, as is not needed here, update the opponent's reference, and finally removing the not from the box overlap call. And to finish off, we'll add true to this return, as at this point we know a collision has been made, but then return false at the bottom as a catch-all, meaning no collisions were found. Now in the update movement function, we'll call this new function and put the result into a has collided variable and return early if this is false. At this point we know a collision has happened, so let's first set the state to collided and reset the animation in preparation for that new state. And as we're using both of the fireball states now, let's add a check at the top of this function to ensure it's still in the active state and exit early if not. This means the animations will still play out, but the fireball will not move across the screen in the collided state. Finally, in the update animation function, we'll add a quick check in the animation completed condition, and if we're in a collided state, call the onEnd function to kill the entity. And just before we check the results, let's ensure Ken's class still marries up with Ryu's. And as we press the light punch button now, you'll notice when the fireball overlaps or hits one of the opponent's hurt boxes, the fireball will change to the collided state and play out that animation before being removed from the scene. Nice. Let's now look to get the opponent to acknowledge in this collision and take damage. At the bottom of the update movement function, we should now look to call the opponent's handle attack hit function, as we know this handles the fighter's hurt state. Or does it? Let's go back to the fighter class and quickly check how we call this function within the update hitbox collided function. We can see it takes an attack strength and a hurt location argument. So let's try this in the fireball class, passing on the time object, but also passing on a heavy attack for the strength and a head hurt location. Having a quick check of the browser, we can see this somewhat works, but not completely. As the fireball collides, the fighter does indeed respond to it, but we're missing a number of things, such as the hurt shake animation and the health damage. This is because all those things are currently being handled within the onAttack hit function from the battle scene class, which we're not calling. Ideally, all these actions should be called from the handle attack hit function call on the fighter class for ease and consistency. Let's look to do just that. Back in the fighter class, let's group the play sound call, the onAttack hit call, and the attack struct setter from the update hitbox collided function and move it to the handle attack hit function. One thing to note, as the on-attack hit function now gets called from the opponent rather than the attacker, we'll need to spot the player ID arguments around so that they marry up again. Also, to make this function work from anywhere, we'll need to add a couple more parameters. These are the attack type, which tells us if the attack was a punch or a kick, and the hit position coordinates for the hit splashes. As we've changed the interface on this function, let's fix the call within the update hitbox collided function first by passing on the new arguments before continuing. Let's go back to the update movement function in the fireball class now and update the handle attack hit call with the new required arguments. We'll use the punch attack type, and for the hit position, as we don't need to spawn a hit splash for this instance, we'll just pass on undefined instead. Although the handle attack hit function within the battle scene class won't be able to handle undefined at the moment, so let's quickly jump back into that function and add a check to ensure the hit position is actually defined before trying to spawn the hit splash, and if not, as per usual, we'll return early. Taking another look in the browser now, when a fireball collides with an opponent, they seem to respond correctly, in that they go into their hurt state, take damage and slide away as intended. Although we're still missing one fireball collision, and that's with other fireballs. You'll notice that they can currently travel through each other, which was never possible in the original game. So to finish off this special move for today, let's add this too. Back in the fireball class, and in the update movement function, we'll look to wrap both of the opponent and fireball collisions with one generic has collided function to make it easier on ourselves. We'll first rename the current reference and go ahead and create the new function itself. We'll then take the first two lines from the original function, which gets the fireball collision box, and move it to this one. We'll then call that function from this function, passing on the hitbox details instead. As we now be looking to identify which collision has happened, we'll return the correct fireball collided state enum value instead of true or false. For that reason, let's remove the false return and replace the true return with the opponent value. Now for the has collided function, its purpose is to return which collision has happened, and if none has, we'll just return undefined instead. So let's use the null coalescing operator after the has collided with component call, and call the new has collided with other fireball function, again passing on the hitbox dimensions. As you can guess, this function will check to see if the fireball has collided with any other fireballs. So we'll now create this new function too. The only snag is that we currently have no way of knowing which other fireballs exist in the scene. Okay, let's make another small refactor to help us with this. If we take a look at the battle scene class, we currently hold and manage all the entities here, including our fireballs. Although we'd ideally prefer to move this into its own generic class, where it can manage its own list. Okay, let's do that. We'll go ahead and create a new file within the engine folder called entity list. Once done, we'll then move the current add, remove, update and draw entity functions over to this new file in class, along with the entity array itself. The entities property within the battle scene class will now be a new instance of this class. Next, we'll look to update and fix any of the current references to the entities to this new structure. Starting with the battle scene class, we'll start with the update and draw functions. We'll fix the current entity calls and use the new entities reference instead, passing on the correct arguments, where we're actually missing the camera now in the entity list class, so we'll fix that too in its own update and draw functions. We'll now update the fighter instantiation, and instead of just passing on the add entity function, we'll pass on the list itself. Then in the Ryu and Ken classes, we'll make the necessary changes there too, replacing the add entity function with the new entity list instance. In fact, the entity suffix on all of the entity list functions are now redundant, so we'll remove those and make the function names a little less repetitive. So we'll again perform some small refactors in the entity list class and the battle scene class where necessary, to keep them in sync. With those changes in place, let's look at the fireball constructor now. Again, let's make it easier on ourselves moving forward and make another small refactor alongside the entity list. Instead of spreading the arguments into the constructor, we'll use an args array instead, while passing on the entity list instance too. This does mean we need to deconstruct the required arguments before we can use them, but this makes the contract between the entities and the construction a little easier to manage. In regard to the fireball class, we'll replace the fighter and strength arguments and deconstruct them from the new args array at the top of the constructor. Having access to the entity list now means we can iterate over it and check to see if we have any further fireballs. But first, let's fix any current references, starting with the on-end calls, and converting them to the new remove function instead. Let's drop back to the entity list now and mirror this change with its add function. We'll remove the spread operator for the args argument and replace the remove function reference with the this keyword, passing on the entity list instead. We'll unfortunately need to make these same changes to the hit splash entities too, but mostly in the super hit splash class. Starting with the constructor, shrinking the parameters to just one args argument, and replacing the onEnd parameter with the entity list argument. Then we'll destruct the x, y and player ID from the args argument, and update the necessary onEnd references with the entity list remove function. Then we'll fix the constructors in the child classes to mirror these changes too. Finally, in the Refactoring classes, we'll now need to use the call sub function on the add function, passing on the entity list reference to ensure we encapsulate the correct this scope. Phew, and we're done. So what was we doing again? Ah yes, fireball collisions. Back to the fireball class then. We can now use the entity list instance and filter it to pull back any other fireball instances within its list. We'll use instance of to pull out any entities matching the fireball class constructor. We'll also ensure we're not comparing with ourselves by checking against the this instance. This should return an array, so if its length is greater than 0, we know there must be other fireballs currently in the scene. If not, we'll just return undefined. We'll next iterate over the other fireballs, and just like the component collider function we created earlier, we'll pull out the collision dimensions from the current frame, and use them in the box overlap function, and compare if it has overlapped the fireball's dimensions. If we do have a collision, we'll this time return the fireball collided state. Next in the update movement function, as we now have multiple collision states, we'll add a check to see if the collision was actually with an opponent, and return early if not. Obviously, if the collision was with another fireball, we wouldn't want to apply the attack hit call. And finally, we'll take another look at the results within the browser. As both fighters performed the special move at the same time, their fireballs will now collide and die as expected. The opponent collisions also still work too, even after all those refactors. Okay, with the fireballs complete, I think we should probably look to correctly implement the way the fighters actually instantiate the special move, with a control combination rather than the light punch button. Before jumping straight into the code however, let's understand how this works. I'm sure most of you know this already, but just to ensure we're all on the same page, I'll quickly explain what a special move is. As you can expect, in Street Fighter, this move requires a little more effort from the player than a standard attack to perform. Generally, this means executing a sequence of unique inputs, which can either be directional inputs and/or attack buttons. These inputs are sometimes called commands, and need to be formed in the correct order and within a small window to be successful. Depending on the fighter's direction and state, can also dictate if or how they can be executed. As we're only tackling the Hadouken special move today, let's take a look at that move specifically with Ryu facing to the right. This move can only be performed on the ground, at least officially, and requires the player to perform a quarter circle motion, from the down direction through to the forward direction on the control input, followed by pressing any one of the punch buttons to complete, which is a far stretch from pressing the light punch button we have at the moment. If we were to list these inputs or commands out, you'd get the following: down, then down forward, and finally forward together with any punch button. Depending on the strength of the punch button pressed, will dictate how fast the resulting fireball will be. As mentioned, these inputs will be performed correctly within a quick motion, but if the player messes up the order or performs the input too slowly, the attempt will become void and you'd have to try again from the start. I should probably mention that there is a notion of charging special moves too, but that is out of the scope of this video series. So knowing how special moves work, how would we put this into code? I'm sure there's a few ways to accomplish this, but this is the way I did it. As we're ultimately looking to check a set of inputs against a known set list of special move commands, we'll need to first record and store the previously pressed inputs so that we can compare them to those predefined special move commands. So this means every input press the player performs will be added to the stack of previously pressed inputs. We'll only need to keep a small subset of these input snapshots, so we can pop the last input from the bottom when the stack is full. Also, as we can press multiple buttons at the same time, alongside the directional inputs, we'll store them individually too. Once this history is available of each player's previous input snapshots, we should be able to easily compare them to any of the special move command sequences. To do this, we'll use a cursor or head to keep track of where in the sequence the player currently is in performing each step. Once the first input matches, we'll wait for the next input in the sequence to be performed to acknowledge the player is attempting to execute a special move. Once in the state, we'll provide a small window for the player to perform any subsequent step. If they press the incorrect input or take too long to perform the next step in the sequence, the cursor will be reset and the player will need to start the sequence again. However, if the player does indeed execute all the sequence correctly, the special move will be performed. As per normal, we use the usual value from array in a state machine to ensure the fighter is able to transition to this new state. Okay, with all those ideas defined, let's now get back into the code and attempt to implement them. To hold the input history for the controls, we'll start by first adding a new module file to the engine folder called control history. Then inside, we'll go ahead and define the actual control history object first. This will be an array of 2 arrays, one for each player. These inner arrays will hold the input snapshot items as objects. Each object will hold the time of the snapshot, the move direction, and an array for all 6 of the attack buttons, which will be false by default. We'll copy this object structure to both inner arrays to present the initial record for each player. Next, we'll create a new function called poll control, which will take a time object, a player ID, and a direction parameter. The purpose of this function is to poll the player's control and store it within the control history array above. From this function, we'll call another function called getCurrentControlSnapshot, which will use the input handler module functions and record a snapshot of the current past inputs. So let's create that now by passing on the same time, player ID, and direction arguments. We'll next create a new temporary polled controls object to store each directional input and call the corresponding input handler function for each. As we can only really press one direction at a time, we'll create another function called getMoveDirection, which will take this temporary object and return the actual currently pressed direction, although it'll probably be best if we create a new enum lookup object first to keep this clean. Okay, opening the fighter constant module, we'll do just that, and call it special move direction, defining each directional key. Notice how we've also defined all 8 possible directions here, which includes the diagonal directions such as forward down. Back in the new control history module, we'll now check each property in the polled controls object and return back the necessary special move direction enum value. Notice how we've prioritised the forward move over the backwards move and the down move over the up move, and if no directional input was found, we'll return none by default. The next thing we need to set up is the attack button array order for the snapshot. We'll create a new array called button order and list out each of the control attacks, starting with the kicks and then the punches, from light to heavy. Now back in the getCurrentControlSnapshot function, we'll return back an object with the timestamp of the snapshot, the special move direction value from the getMoveDirection function, and finally the buttons array, where we'll map over the button order array we just created and use the isControlDown function to check to see if the corresponding button is pressed. This will return an array of true or false for all the buttons listed in this array. Now that we have a complete input snapshot, before we go ahead and insert into the control history object store, we'll first make sure this snapshot is different than the previously stored snapshot, as we only want to store those changed states rather than a snapshot every frame. We'll create another function called isLastSnapshotDifferent, passing on the snapshot we've just collected, along with the player ID. Let's now simply compare this snapshot with the last snapshot we retrieved by matching the move and button properties individually. We'll use the array's sum function on the button array to make this compare a little more efficient. This function will return true if the snapshots are different and false if they are not. Finally, back in the poll control function, we'll continue on if we have a valid snapshot. To ensure we got a stat-like ordering, we'll use the array's unshift function and insert the latest snapshot into the control history on top. Let's also ensure we count the amount of snapshots we store here by popping off any snapshots when the length is higher than 10 records. We'll store this cap within its own constant variable to remove the hard-coded value. And that should be enough to test this now. Let's jump over to the battle scene class, and in the update fighters function, we'll call this new poll control function within the for loop, passing on the time, the fighter ID, and its direction. So this means as the fighters are updated, we'll now also poll the controls and update the control history object. Let's open up the input handler module now and amend the isButtonDown and isButtonUp functions by null coalescing the results with a false value to ensure they work correctly with our new control polling function. And just before we test these changes, we'll drop back into the poll control function and log out any valid control snapshots for Ryo's controls to the console so we can see what's happening. Opening up the browser then, we'll drop into the DevTools and watch the console window while controlling Ryo around the screen. Notice how the poll control function is now logging each snapshot to the console window, recording the game time with each. Let's investigate a couple of these to see exactly what is being recorded. Opening up the first object, you can see this has both the move and buttons array with their default values. An object like this means the player is idle and has therefore released the control. Pairing that snapshot to the next one, notice the third button in the list is true, which means the player has pressed the light punch button. Let's now clear the console and try to replicate the Hadouken command movement now. As you can see in the snapshot messages, we have the correct sequence in the logs here. Starting with the move property, we have the down, and forward in the correct sequence, one after the other. If we open up the following one, you'll notice this time we have button 6 set to true, which is the heavy punch button. Even though I was a little late with this punch button, you can see from the timestamps it was still within the allowed window of 150 milliseconds, which means we would have still performed the special move. So far so good. It would seem we're recording the controls as required, meaning we can continue on and set up the special move command sequences. Starting with the Ryo class, we'll add a new property called Special Moves. This will be an array of objects, which will hold the required details for each special move, specific to each individual fighter. The objects themselves will have a state property, that refers to the resulting state the special move will trigger, which we know in this instance will be special move 1, and a sequence property, which will hold the actual command list in the order the control input should be performed, although we currently only have the directional move set up in an enum at the moment. Before moving forward, we'll also need to do the same for the buttons too, so that we can complete the Hadouken special move sequence. Back in the fighter constant file, we'll create a new enum object called special move button, and add two keys called any punch and any kick. Both of these are special move only button values that allow us to use any of the tap buttons in the command sequence. As we know the Hadouken special move is executed with any punch button, we'll now go ahead and use the any button value from this new enum object to complete the sequence. Finally, we'll add a cursor property too, which will hold the position or index in the sequence the player is currently at, if any. This will have a default value of 0, which is the start of the sequence. And that should be enough to work with. So now in the fighter class, we'll create a new function called update special move, and add it to the main update function. The purpose of this function is to iterate over the fighter's special moves array, and check to see if any of them have been successfully executed. Although we don't have anything that does that just yet, so back in the control history module, we'll create another function that does this for us. We'll call this has special move been executed, funnily enough. This will take a special move object from the fighter's special move array, the player's ID, and the current time object, which we'll need to ensure we're in the allowed time window. Inside this function, we'll again call another function called has control matched, which will check the last control history snapshot against this special move sequence based on its cursor. This will return undefined if they do not match, but return true for if they do. Here we'll use a switch statement on the control argument so that we can perform different checks based on the special move control inputs. We'll first start with the any punch special move button value, and therefore iterate over the last 3 button values in the snapshot, as we know they relate to the punch attacks. If any of them are true, we'll return the actual punch button that was pressed, using the button order lookup array. Next we'll do exactly the same, but with the kick special move button value, iterating over the first 3 button values this time. Again, returning the actual kick button, using the button order array if any of them are true. For the directional move property, we'll just use the default keyword here, and simply check if the last snapshot's move property matches 1 to 1. If they do, we'll return true. And lastly, if none of these moves match, we'll return false. Back in the has special move completed function, we can check to see if this function has returned a truthy value. If it's returned false, we'll first ensure it's still in the allowed time window of 150 milliseconds, using the last control history snapshot's time property, comparing it with the time object we've passed in. Let's add this time window to its own move delay constant value before moving on, however. We'll also check to see if the current special move cursor is higher than 1, the second index, to allow for charging, to replicate the behaviour of the original game. If both of these are true, we'll reset the special move cursor back to 0, the beginning, and return false. At this point we know the control is matched, so we'll next check to see if the cursor is at the end of the sequence, meaning the special move input has been completed. If so, we'll return the truthy value from the control match function. We'll come back to the reasoning behind this in a second. And finally, we now know we're still midway through a special move sequence at this point, so we'll increase the cursor for the next cycle, and again return false, knowing the special move has yet to be completed successfully. Now back in the fighter class, let's complete the update special move function. We'll call the new has special move been completed function, passing on the special move details, the player ID, and the current time object. This will return, as we know, the result from the control match function, if it is truthy, which we therefore also know will possibly be a punch button control or a kick button control. We've done this on purpose as we now know which button was used to execute the special move, meaning we can use it to initialize the special move state. We'll do this on the change state function, and add another parameter to it called args. This now provides us with a way to pass an initial payload to initialize any of the states within the state machine. Specifically for us, we can use this value to determine the strength of the fireball we need to execute. So moving on, we'll call the change state function if the result args value is truthy, and use the special move state property for the state we wish the fighter to transition to, passing on the time and the result args arguments. Let's amend the change state function now, adding the new args parameter to ensure we pass the special move result. We'll then add this to the init call. We can now go back to the Ryo class and add a new parameter to the handle Hadouken init function and call it strength. Notice we've again used the underscore as the first parameter here, as we don't need a time property in this function. Before we can test what we've done, let's go ahead and copy the Ryo class special move changes to the Ken class to ensure they both match. Oh yes, and finally, before we forget, we should also now be able to refer the light punch attack change state we made earlier in the video. Okay, let's open up the browser and see what we've accomplished. If we press the light punch button this time, you can see we've restored the light punch move to how it was at the beginning of the video. More importantly, however, if we also perform the correct input sequence for the Hadouken special move, down, down and forward, plus any punch button, we will actually execute the move and produce the fireball. Let's quickly open up the dev tools and check the console log to confirm this. Let's perform this move once again, and as you can see from the logs produced, the special move sequence is clearly listed and matching what is expected, resulting in the fighter successfully transitioning to the special 1 state, producing the fireball. Notice that depending on the punch button used, the fireball travels faster across the screen. So this is perfect, everything looks good. In theory, the same process can be applied to all the special moves that we have for all the fighters, as long as we know the correct input sequence and apply the state machine logic to it, but that's one for another day in video. And just before we close up for today's video and series, let's finish up with a few additions and the usual refactors. We'll start today's refactoring section, small and simple, by moving the canvas's dimensions back to the code to help remove some of the hard-coded values we're currently using. In the game constant file, we'll add both the screen width and height dimension values and export them. Now in the constant helper module, we'll set these values to the canvas on the context dimensions in the getContext function. This change will replace the hard-coded values we currently have on the canvas element. We can now go back to the element in the HTML file and remove those attributes as they are no longer required. Let's now perform a search on all of our code for any instances where we've either used the hard-coded screen dimensions or the canvas directly. This includes the stage constraints function in the fighter class, the same in the camera class, where we are applying the scrolling constraint, in the fireball class, where we're checking the edges of the screen, and finally in the battle scene class, where we reset the camera. For the next refactor, let's apply our visual debugging drawing to the fireball entity as well. In the fighter debug module, we have 2 functions that cover drawing boxes and crosses for the origin points. Let's cut these from this module and move them to their own generic entity module, called entity debug. Once these have been exported, we'll import them back into the fighter debug module. Next, we'll move on to the fireball class and apply those functions there too. We'll import all the exported functions under the debug alias, as we've done before. Then moving on to the draw function, we'll start by deconstructing the collision dimensions, and then add a call to the draw box function, passing on the necessary arguments, using the common red colour as the attack collision box. We'll also add the draw cross call for the fireball's origin point too, using white as the colour. While on the subject of debugging, let's now add a way to toggle these values on and off. Back in the game constant file, we'll add a new boolean value called enable debug. For the moment, we'll set this to true, as we currently want to apply debugging information. Then in the fireball class, we'll simply check if this value is not true and return early, skipping the debug calls. We'll also do the same in the fighter class for its own debug calls. Although in this class, we'll also apply the same check within the handle attack hit function above the console log message. Oh, and before we forget, let's also now remove the console message we added in the control history module in the poll control function, as we've proven this now works as intended. Thinking back, we could also simplify the valid from additions within the Ryu and Ken classes. Instead of using a spread, we could probably just use a push instead here. Let's make that change too. Let's quickly check the browser before moving on, and test to see if everything is working as intended. Luckily for us, it does indeed seem so. Notice we now have the visual presentation of the fireballs too. Nice. Okay, back in the game constant file, let's switch the debug visuals off, and perform another check to see if this still works too. And again, it seems so. All the visual debugging has been removed, giving us a much clearer view of the game. Although we still have a minor issue that I'd like to fix before we close up for today, and that's around the slider mechanic. Notice when Ken is at the edge of the screen and one of Ryu's fireball collides, Ken's hurt slide velocity will still be transferred to Ryu, which is incorrect. So for the last change of the series, let's fix this. In the fighter constant file, we'll add a new enum object called fighter hurt by, adding 2 properties, one for the standard fighter hits and one for the fireball hits. Then in the fighter class, we'll start in the handle attack hit function and add a new parameter called hurt by, which will pass on what caused the actual hit. Here, we'll set a new local property with the same hurt by name, so that the fighter will record this. Back at the top of the class, we'll add this to the constructor variables and set it to undefined by default. Now in the handle hurt state function, in the same section as the other hurt properties, we'll reset it back to undefined for the next attack hit. We can now go ahead and update the handle attack hit calls and add the necessary hurt by enum value. In the update hitbox collided function, we'll add the standard fighter value, although in the fireball call, you guessed it, we'll add the fireball value to the call in the update movement function. Back in the fighter class, and its reset slide function, we can simply now extend the transfer to opponent check to include this hurt by property and ensure it was caused by a fighter before proceeding to transfer the slide velocity to the opponent. And with that final change, let's have a quick check in the browser to see if this worked. We'll push Ken to the furthest right side of the stage and attack him with the various standard kicks and punches. As per normal, Ryu will slide away as expected. But let's now try with a fireball. Notice this time that Ryu will not be affected. Perfect, it looks like this final change is working. So with that, I think that's where we'll leave it for today. Let's quickly review what we've achieved. We initially fixed up the camera so that the stage scrolled based on the fighter's position, rather than their velocity. This made it behave more like the original game, especially when it comes to the sliding effect. We then got into special moves, adding the Hadouken move to both Ryu and Ken's state machines. We accommodated the shadows too, and added the necessary sound changes. This in turn meant we added the fireball entity that spawned when successfully performing this move. Finally, we also delved into input sequences, and added the ability to record the player's control device. This was so we could compare these to a predefined command list, executing special moves. As this is the last part in the series, I've hopefully gone over all the fundamentals of building a Street Fighter game in JavaScript. This leaves the game as a perfect foundation to be extended, either to be a complete remake, to be amended to either your personal fighting game or something entirely different. If nothing more, you should now at least have all the basics to build your own browser games. And there you have it, the longest video to date, and hopefully a good place to tie the knot. I'll be calling it there, at least for the time being I guess. As mentioned, I do have other ideas on how to extend the series, but I think we're in a perfect place to take a little break from it. As for next month, I'll be continuing to update the game, adding the missing parts such as blocking, throws and dizzy states. But this will be for patrons only for the time being, which will lead into possible future video ideas, such as CPU controlled fighters. So expect the occasional part to be added to the Street Fighter series in the near future, but these will be far more spaced out than usual from now on. My main focus will be to move on to other things and potentially produce more generic game related content, making it more YouTube friendly I guess. I'll also possibly be looking to start another game soon, but more news on all of this to come. I've had a great time putting this series together and I've learnt a lot along the way, so I'll hopefully be putting some of that into my future content. And finally, just before we close up for today, I'd first like to apologise for my pronunciation of Hadouken. I'm sure I've completely butchered it. But honestly, once again I'd like to thank everyone who has subscribed, followed or liked any of my videos in the series. I'm amazed at the support and how well these videos have been received, especially as this is my first ever tutorial series. I honestly never would have thought this was possible, both on this channel and on my Patreon page. So a big shout out to all my Patreon supporters here, you guys really do spur me on the most. And with that, I'll say my goodbye and I hope to see you in the next one. And out.